Swayam Prabha. Digital India. Educated India.
Hello and welcome. Let me ask you one question. Consider two periodic signals x1 like this with a time period of t1 equal to 3 seconds and x2 like this with time period t2 equal to 4 seconds. Now consider the sum of x1t plus x2t. The question is whether x1 plus x2 is also a periodic signal or not. And if it is a periodic signal, then what will be the time period of x1 plus x2? The answer to the first question is, of course, yes, because x1 repeats itself after every 3 seconds, x2 repeats itself after every 4 seconds. Therefore, if you consider the LCM of T1 and T2, that means least common multiple of 3 and 4, that is 12, then after 12 seconds, both x1 and x2 will come back to their initial positions again. And after 12 seconds, everything will start to repeat from the beginning. This also says that the time period of x1 plus x2 will be the LCM of T1 and T2. So in this way, if you consider many periodic signals with time period T1, T2, T3, T100, T1000 and like that, then when you add all these signals, the time period of the mixed or added signal will be the LCM, least common multiple of T1, T2, T100, T1000, all of them together. So when we add 100 or 1000 or 10,000 periodic signals, the result is going to be again a periodic signal. Now, previously we have seen that almost any periodic signal can be created by mixing or adding sine and cosine signals only, or mixing only complex exponential signals. Today, let me ask, can we also create aperiodic or non-periodic signals also by mixing periodic sine, cosine or exponential signals? Apparently, the answer is no, because it looks like if we add 100 or 1000 periodic sine, cosine or exponential signals, the result will also be a periodic signal. But actually the answer is yes. It is possible to create even aperiodic signals by mixing periodic sine, cosine or exponential signals. And the main idea, main catch is this. We know a periodic signal is a signal that repeats itself after every t unit of time. And an aperiodic signal is a signal that never repeats, or we may say that repeats after infinite amount of time, after infinite amount of time. So that is a mathematical way of saying that it never repeats. So we can say that an aperiodic signal is also a periodic signal with time period infinity. Again, an aperiodic signal is a periodic signal with time period infinity. That is the catch. Now let us consider two periodic signals with very close time periods, like one having a time period of 3 seconds, another having a time period of 3.1 second. Now, if you add these two signals, then the time period of the mixed signal will be the LCM of 3 second and 3.1 second, which you may also write as the LCM of 3000 millisecond and 3100 millisecond, and that will be, if you calculate, 93,000 millisecond or 93 second. So this number is a number much larger than the two individual time periods. In the same way, if you consider, say, t to be equal to 3 second t1 and t2 to be equal to, say, 3.001, then the LCM of 3 second and 3.001 second, that means LCM of 3000 millisecond and 3001 millisecond will be 9003,000 millisecond or 9003 second, which is quite large. In this way, if you make the gap or the difference between these two time periods even smaller, then you can create a periodic signal by adding these two, which will have an even longer time period. And in the extreme case, if you want to create an aperiodic signal, that means a signal with time period infinity, you have to mix signals whose time periods differ by very small amount or infinitesimally small amount. That is the second thing to learn today. By mixing signals whose time period or frequency differs by a very small amount, we can create a signal whose time period will be very large. In this way, by mixing signals whose frequency or time period differs infinitesimally, we can create actually an aperiodic signal, that is a signal with infinitely large time period. Now, the third thing that we will learn is this. Consider a periodic signal with, say, frequency equal to 50 Hertz. That means omega fundamental angular frequency equal to 2 pi into 50 radian per second. If we perform a Fourier series of for this given signal, then we will get many harmonics, and amount of those harmonics we can show using a magnitude spectrum. Suppose this is the magnitude spectrum, we will have harmonics corresponding to n equal to 0, that is the DC or average component, then n equal to 1, that is the first harmonic or the fundamental component, n equal to 2, 3, 4, etc. Also on the other side, n equal to -1, -2, -3. For all these values, we will have some harmonics. And the frequency of these harmonics will be 50 Hertz for the first harmonic, 100 Hertz for the second harmonic, 150 Hertz for the third one, and so on. 0 Hertz for the average component, and so on. And the corresponding omega values or angular frequencies will be 0, 2 pi into 50 radian per second, then 2 pi 100 radian per second, and so on. And then we put vertical lines or bars to denote the amount or amplitude of these harmonics, like this. So this way we get a discrete graph, not a smooth continuous graph, discrete bar diagram, you can say, which says that these are the different frequencies or components present in this signal. However, there is no component present in this signal which has a frequency between 50 and 100 Hertz or between 100 and 150 Hertz. Those frequencies are absolutely not present. Now, if you consider another signal, say with a frequency like this, say this frequency is 25 Hertz, half of the previous frequency, then if you perform the Fourier series for this signal, you will get components at 0, at 25 Hertz, then also at 50 Hertz, 75 Hertz, 100 Hertz. All these values can be present if you perform the Fourier series on this signal having a lower frequency. In this way, if you consider a signal with even smaller frequency, maybe 5 Hertz, then that will have components with frequency 0, 5 Hertz, 10 Hertz, 15 Hertz, 20 Hertz, 25 Hertz, 30 Hertz. All these components will be present in this signal having a frequency of 5 Hertz. This way you observe, as we keep decreasing the frequency of the signal, in the spectrum we get more and more lines, more densely packed, having frequencies which also differ from one another by a relatively smaller amount. That means if you have a periodic signal with very large time period, then in its spectrum we will have components whose frequencies will differ by very small amount. In fact, for a aperiodic signal or a signal with infinitely large time period, in the spectrum we will get components or harmonics having frequencies differing by almost nothing or differing by negligible infinitesimal amount. And that is also required because we have learned to create a signal of infinite time period, we need to mix signals with frequencies differing by very, very small amount. So this is the third thing to learn. Now let us do some mathematical jugglery. Okay, consider a given signal xt and then uh, take a signal e to the power minus j omega t for some value of omega, whatever you like, whatever you choose. And then let us define the following quantity. First, we shall multiply the given xt with the e to the power minus j omega t that you have chosen. Then we shall integrate the product over time t equal to minus infinity to plus infinity. Now after this integration, the variable t will be gone and the result of this integration will only depend on the value of omega. So we can call this as a function of omega. Call it capital X of omega. Capital X because it depends on small x, that is the given signal. Okay, so this is the definition of a new quantity, capital X of omega, as the integration of xt e to the power minus j omega t dt from minus infinity to plus infinity. Now we know that for periodic signals we can calculate Fourier coefficients Cn in this way: integration of the signal xt multiplied with e to the power minus j omega n t dt, t running from minus infinity to minus t by 2 to plus t by 2, that is one complete cycle, and then divided by the time period t. This way we can calculate the Fourier coefficients of a periodic signal. And once we know these Fourier coefficients, then we can write the given signal xt as a sum over Cn e to the power plus j omega n t, n running from minus infinity to plus infinity, where this omega is equal to 2 pi over t, the time period of given x. Now suppose x is aperiodic. That means it is periodic with time period very large tending to infinity. That means the frequency is 1 over t that tends to 0, and the fundamental angular frequency omega is 2 pi over t that will also tend to 0. Let me use a different symbol in place of omega. Let me write delta omega, so that it reminds me that the value of this quantity is close to 0. Although the definition is same as before, is same as usual, 2 pi over time period. This delta symbol only to remind me that the value is close to 0. Then for this xt, I can calculate Fourier coefficients in the usual way, except that I will use the symbol delta omega, where delta omega is 2 pi over t, which tends to 0. And once we have these Fourier coefficients, then we can write the original signal xt as a sum of complex exponentials, except that now I have to use delta omega, where delta omega is a very, very small number. Okay, then let me put the expression for Cn from here in this equation. So I will write sum over n equal to minus infinity to plus infinity. In place of Cn, I shall put this expression 1 over t integration of xt e to the power minus j delta omega n t dt, t running from minus t by 2 to plus t by 2, one complete cycle, and this is Cn. After that I have this e to the power j delta omega n t, right? Okay, and also let me put here that limit t tends to infinity and delta omega tends to 0. This is x of t. Now let me write this as limit t tending to infinity delta omega tending to 0, and we have a sum from n equal to minus infinity to plus infinity. In place of t, let me write 2 pi over delta omega, and then the integration of xt e to the power minus j delta omega n t dt. In place of minus t by 2, let me put minus infinity and here plus infinity. And this quantity is also there, e to the power j delta omega n t. This is nothing but x of t. Now let us go back a bit and look at the definition of capital X omega that we have defined. From this, if you put in place of omega delta omega n in the left hand side, then you have to also put in place of omega delta omega n in the right hand side, like this. Now you look at this quantity. This is exactly what we have here, right? So that means this thing is capital X of delta omega n, and let me keep all other terms as it is. I need not write t tending to infinity because there is no capital T here. So it is enough to write delta omega tending to 0. This is x of t. Now let me put this 2 pi outside, that is a constant, and then we have limit delta omega tending to 0, a sum over n equal to minus infinity to plus infinity. Here we have x of delta omega n e to the power j delta omega n t and this delta omega. Now this infinite sum with this infinitesimal small value of delta omega, this can actually be written as a integration like this, 1 over 2 pi as it is, and then this sum will become a integration over x of variable omega, some variable, and then e to the power j in place of delta omega n, again put omega, then in place of delta omega put d omega, and omega running from minus infinity to plus infinity. Okay, this is because if you recall the basic Riemann's definition of integration, if you have a function say f of x, you want to integrate it over x from x equal to minus infinity to plus infinity, that is same as doing this sum sum over f of n delta x n running from minus infinity to plus infinity and delta x tending to 0. This is like if you have the signal f of x, this integration in the left hand side is nothing but the total area under this curve that you can calculate by slicing this into small slices or intervals delta x, and then you calculate the area under area of each of the slice and you add. So the area of any slice can be written as the height of the function at that point multiplied with the width delta x, and then you sum over all the slices, that is n from minus infinity to infinity. That is the Riemann's definition of integration, and using this idea xt can be written as the integration of this thing. Okay, so what have we got? We have written xt as integration of capital X omega e to the power j omega t d omega, where capital X omega is defined here, right? Xt e to the power minus j omega t dt integrated from t equal to minus infinity to plus infinity. So we have written an aperiodic signal xt in this way, 1 over 2 pi this thing, integration of capital X omega e to the power j omega t d omega, omega running from minus infinity to plus infinity, where this quantity capital X omega was defined earlier here. Okay, it is integration of small x t e to the power minus j omega t dt, t running from minus infinity to plus infinity, and there is no 2 pi term here. This quantity x of omega is called the Fourier transform of small x t, and small xt is called the inverse Fourier transform of capital X omega. It looks like that if small xt is given, using this formula you can calculate capital X omega. And if capital X omega is given, then using this other formula you can calculate small xt. So that means knowing one is equivalent to knowing the other, and these two are called a Fourier transform pair, x small xt and capital X omega. Note that capital X is a function of omega, where omega has the unit of frequency radian per second, and small x is a function of t, which has a unit of time or second. Now these formulas have a very nice physical meaning. Look at this first formula. According to this, xt can be written as a sum of complex exponential, because integration is also a kind of sum, and we are adding many e to the power j omega t terms for different values of omega. More importantly, this omega can take any value, any continuous value, because this integration is performed over a continuous range of omega. X omega is defined for a continuous range of omega, not necessarily only for integer multiples of a fundamental frequency. No, here capital X omega is defined for any fractional value of omega, and therefore we are adding or mixing e to the power j omega t for any fractional or integer or any type of value of omega. So this means that xt can be created by mixing periodic e to the power j omega t type of signals, even when xt itself is aperiodic. And omega is not restricted to take only integer multiple values of any fundamental frequency. It can take any kind of fractional values. If you go back to our earlier discussion, we said that if you consider a periodic signal with smaller and smaller frequency, then in its spectrum we will see harmonics or components which are densely packed. And in the extreme case, when you consider a non-periodic, aperiodic signal, then these harmonics will be so densely packed that there won't be any gap between two consecutive components or harmonics. That's what we are now seeing in our Fourier transform formula, that omega can take any fractional value, not only integer multiples of some fundamental frequency. Okay, so this is the time for an example. Consider this rectangular pulse x of t with height or amplitude a starting at t equal to minus d by 2 and stops at t equal to plus d by 2. The signal is aperiodic. It does not repeat itself. It is 0 ever before time minus d by 2 and it is also 0 ever after time plus d by 2. So it is not repeating at all. Now let us calculate the Fourier transform of xt, which we will denote as capital X omega. According to the rule, it is given as xt e to the power minus j omega t dt integrated from time equal to minus infinity to plus infinity. Now, since this signal is 0 beyond this range of plus or minus d by 2, we can write it as integration from minus d by 2 to plus d by 2, because beyond this range the signal is 0. And also within this range x is constant with a value of a. So let me put a in place of x and then e to the power minus j omega t dt as it is here. Now this can be written as a constant common outside, and integration of e to the power minus j omega t is e to the power minus j omega t divided by minus j omega with limits plus d by 2 and minus d by 2. This will be equal to a, then e to the power minus j omega d over 2 minus e to the power minus minus will be plus j omega d by 2 and then minus j omega in the denominator. Now this you can write as a, you can put you can make it plus and a minus here, then this 2 will together with this j will give us 2 sine omega d by 2, and we shall have omega in the denominator. This you can also write as a sine omega d by 2 divided by omega. This 2 I shall put downstairs like this, and then let me multiply and divide with d. That is the answer. Not quite correct, because you cannot do this integration in this way if omega is equal to 0. So this is true only if omega not equal to 0. Otherwise, this formula of integration is not valid. Divide by 0 makes no sense. But if omega is 0, we can calculate x omega even more easily. So x0 in that case will be equal to a e to the power 0, that then dt integrated from minus d by 2 to plus d by 2, and e to the power 0 is 1, so you will get a constant, and this will become d. Basically this is nothing but the area under this curve, which is same as the height multiplied with the width d, ad here. Okay, now combining these two results for omega non-zero and omega being 0, we can write finally x of omega is equal to, from here, ad sine omega d by 2 divided by omega d by 2 if omega is not 0, and otherwise it is ad only. It is ad if omega is equal to 0. There is a simpler way of writing this. Uh, you probably know that there is a function called sinc function, SINC, and by definition it is defined in this way: sinc x is equal to sine x divided by x if x is not equal to 0, and this is equal to 1 if x is equal to 0. Okay, and then from this definition you may write this as AD. AD is common in both the cases, and if omega not equal to 0, we have sine omega d by 2 by omega d by 2, and if it is 0, we have here 1. So this and this can be written together as sinc, SINC, of omega d by 2. So this is the final answer. This is the Fourier transform of this rectangular pulse. Next, let us plot this function x of omega, capital X of omega, as a function of omega. Suppose this is the omega axis, and we are going to plot this function ad sinc omega d by 2, which is same as ad sine omega d by 2 whole divided by omega d by 2, provided omega is not 0, and if omega is 0, then this is equal to AD. Okay, now let me first draw sine omega d by 2. So a sine function will look like this. This is sine omega d by 2, and let me now plot 1 over omega d by 2. So that will look like this. Okay, so this is 1 over omega d by 2. Now you have to multiply these two, and if you do that, then it will look somewhat like this. and at omega equal to 0, this will become 1, uh, which is also same as the limit omega tending to 0 sine omega d by 2 divided by this. If you take the limit omega tending to 0, this is also 1. So it will be somewhat like this, and the left side will also be symmetric to the right side, because this is the even function. Sine is an odd function, 1 over omega d by 2 is an odd function, and product of two odd functions is an even function. And finally you have this constant AD multiplied to the everything. So this height will be AD. So this is how the sinc omega d by 2 multiplied with AD is going to look like. Okay, and this is equal to x of omega, Fourier transform of xt. And this graph is actually the spectrum, frequency spectrum of x small xt. Okay, in fact, if you take a modulus of x omega, that we will call as the magnitude spectrum. If this is capital X omega, then when you take modulus of that, then this negative part will become positive, like this. This also will become positive. And this part will remain as it is, and that is how modulus of x omega is going to look like as a function of omega. So this is the magnitude spectrum. This non-periodic rectangular pulse can be created by mixing periodic complex exponential signals with different frequencies. And what are the amounts of different frequency components present in this signal xt? That can be determined from the spectrum of the signal or the magnitude spectrum of the signal. Please note that unlike the spectrum of a periodic signal, this is not discrete in nature. This is not made up of discrete bars or lines. Rather, this function is a continuous function of omega. That means all frequencies, all different omega values are present in the aperiodic rectangular pulse. Now, in general, an aperiodic signal xt may be written as a sum of periodic complex exponential signals of the form e to the power j omega t with amplitude or amounts that depends on the frequency. Call this capital X of omega, and let us mix them all or add them all or integrate over all possible frequencies, omega equal to minus infinity to plus infinity. This way, by mixing complex exponential signals, you can create aperiodic signals. And to determine the amount or amplitude of different frequency components, that is capital X omega, you can use this rule. Capital X omega is equal to xt e to the power minus j omega t integrated from time minus infinity to plus infinity. This capital X of omega tells us what are the different amounts of different frequency components present in this small xt. This is also called the Fourier transform of the signal small xt, which we denote with this curly f, f for Fourier transform. So given a signal, you can calculate its Fourier transform using this formula. That means you can calculate what are the amounts of different frequency components. Also, if you know the Fourier transform, that means if you know capital X omega, that means if you know what are the amounts of different frequency components, then from that you can get back the original signal using this first formula, which we call as the inverse Fourier transform, F inverse of capital X of omega. Now, next we shall study some important properties of Fourier transform. First of all, if x omega is the Fourier transform of a signal small xt, and if this small xt is real valued, which is always the case in practical life, then x of minus omega will be equal to x of plus omega star complex conjugate. The amplitude of the component with frequency minus omega will be complex conjugate of the amplitude of the component with frequency plus omega. This is very easy to prove. You know that x of omega is given as the integration of xt e to the power minus j omega t dt, t equal to minus infinity to plus infinity. And therefore, if you want to calculate the value of the Fourier transform at minus omega, you have to put minus here in the right hand side. And then this is nothing but xt e to the power minus j omega t dt conjugate of this from t equal to minus infinity to plus infinity. Because when you take complex conjugate, you have to put minus j in place of j everywhere. But x is real, so there is no j inside x, so only place you have to put minus is here, and that is exactly what we have here. So this is equal to integration of xt e to the power minus j omega t dt from minus infinity to plus infinity whole conjugate. And this is by definition x omega whole conjugate, because the term inside the bracket is capital X omega. And you know this is required because we need in the spectrum the component with frequency minus omega and with plus omega, both to be present with amplitudes which are complex conjugate to each other, because these complex exponentials are like spirals that rotate in three-dimensional space we have discussed, and the one with positive frequency rotates in the opposite direction to the one with negative frequency. If and only if their amplitudes are same and they start from symmetric opposite position, then their imaginary part will cancel and only the real part will remain. That is required because the given signal xt is real. Next property, if xt is even, then capital X omega will also be even. In the same way, if xt is odd, then capital X omega will also be odd. Let us prove it. Suppose consider capital X of minus omega. This is given as xt e to the power minus j minus omega t dt from minus infinity to plus infinity. Now let us put minus t is equal to tau. Then we shall have x of minus tau and e to the power minus j. This minus minus I can write as plus j omega, and in place of t let me put minus tau. Okay, and this implies that dt is equal to minus d tau. So here I will put d tau with a minus sign, and the limit of integration will change. T runs from minus infinity to plus infinity, so tau will run from plus infinity to minus infinity. So this will become plus infinity to minus infinity. Next, this you can write as, let's consider this minus sign and change and swap the limits of integration. So we will write minus infinity to plus infinity, x of minus tau e to the power minus j omega tau d tau, and tau being a dummy variable, in place of tau you can easily put any other variable like t. Okay, and now this will be equal to, there are two possible cases. Number one, if xt is even, then x minus t is same as x plus t, so it becomes x plus t e to the power minus j omega t dt from minus infinity to plus infinity. If x is even, and if it is odd, then x minus t is same as minus of xt, so put a minus sign here. This is if x is odd, and now you can see this is nothing but by definition capital X omega, and this is nothing but by definition minus x omega. This is if x is even, and this is if x is odd. Okay, and the left hand side is x of minus omega. So you see, if x is even, x minus omega is equal to x omega, so a capital X is also even. And in the same way, if small x is odd, capital X minus omega is minus of capital X omega, so capital X is odd. As a corollary of the previous two properties, you know, capital X omega is complex in general, and you may write it as A omega plus J B omega. A is the real part and B is the imaginary part. Now, see if x is real valued, which is always the case in practice, then x of minus omega should be equal to capital X of plus omega star, which means A omega plus, A of minus omega plus J B minus omega should be equal to A omega plus J B omega whole star, and the right side is A omega minus J B omega. This conjugation makes plus J into minus J. Now comparing the real and imaginary parts from the left and right side, you can see that A minus omega should be equal to A plus omega, and B minus omega should be equal to minus B plus omega. That means A is even but B is odd. That means if the signal is real valued, then A, that is the real part of the Fourier transform, will be even, and B, that is the imaginary part of the Fourier transform, will be odd. Now, suppose x is both real and even. Now, x real implies B is odd, that is the imaginary part of the Fourier transform. B is odd because x is real. And since x is even, capital X should also be even by virtue of property number 2. Now that means B is odd and X is A plus JB, that is even. That means A and B both should be even. So since X is real, B should be odd, but since X is even, B should be even. Now how that is possible? The only possibility is that B is equal to 0. Then B is simultaneously odd and even. So that means the imaginary part of the Fourier transform x omega will be equal to 0, or x omega will be real, purely real. In the same way, you should prove if x is real and odd, then capital X of omega will be purely imaginary. That is, the real part of capital X omega will be 0. This is your homework. Next, property number 4. This is very easy. We know that X omega is equal to e to the xt e to the power minus j omega t dt integrated from minus infinity to plus infinity, implying that x of 0, capital X of 0 will be equal to xt e to the power 0 is 1 dt minus infinity to plus infinity. That is the area under the curve xt. Okay, and in the same way, we know that small xt is equal to 1 over 2 pi integration capital X omega e to the power plus j omega t d omega from minus infinity to plus infinity. So therefore, small x0 will be equal to 1 over 2 pi integration of capital X omega e to the power 0 is 1 d omega minus infinity to plus infinity. So from this you can say that the area under capital X omega, that is this integration, is equal to 2 pi times small x 0. So that is very easy. The next few properties that I will show you, you should try to prove them yourself. So I shall first write the property. You will first try to prove it yourself. If you have any difficulty, only then you will watch the video. Otherwise, you will do it yourself. Okay, so next property is this. If the Fourier transform of a signal xt, which we will denote with this symbol, is capital X of omega, then the Fourier transform of k times xt will be equal to k capital X omega. Try to prove it yourself, and here is the proof. Fourier transform of k xt is by definition integration of this signal k xt e to the power minus j omega t dt time from minus infinity to plus infinity. Now this k is a constant, so you can write it outside the integration, and inside you have xt e to the power minus j omega t dt from minus infinity to plus infinity. And this is equal to k. This integration is nothing but capital X omega. Okay, that was easy. Next, again, if the Fourier transform of xt, small xt, is capital X omega, then the Fourier transform of x minus t will be equal to capital X minus omega. This is time reversal property. Try to prove it yourself. And here is the proof. Fourier transform of this x of minus t is by definition integration of x minus t e to the power minus j omega t dt from minus infinity to plus infinity. Now let us put tau equal to minus t, then this will become x plus tau e to the power minus j omega minus tau, but I will put the minus sign here without any problem, and dt will become minus d tau. Okay, so d tau is same as minus dt, and the range of integration will change. It will become plus infinity to minus infinity. Now again you can swap the limit of integration with the help of this minus sign. So that will become plus integration of minus infinity to plus infinity x of tau e to the power minus j minus omega tau d tau. Tau is a dummy variable, so if you want you may replace tau with t, then this is what we have, and this is nothing but capital X at minus omega. This is since x of plus omega is equal to integration of x t e to the power minus j omega t dt, t running from minus infinity to plus infinity. So if you put minus omega here, here also you have to put minus omega, and exactly that is what you have here. Okay, so that is all for today. Next day we shall prove a few more important property at the beginning, and then we will move on.